Hello and welcome everyone. So we had started our discussions on learning algorithms. So I said there is a problem, there is some data associated with that, and you have to somehow train a model. So now what we did is initially we trained our model randomly by random guessing. So basically by model learning we meant that you have this W and B, that is weights and biases, you want to learn them. So you started with some initial W, okay, and you started with some initial bias. So we called these as parameters. Let's call these as theta. So these were theta was the parameter that we had, okay, and we wanted to learn some optimal thetas. The theta was a vector which contains W and B. So we want to learn delta theta. So what was delta theta? This was change in W and change in bias. Okay, so somehow we want to learn the direction. So if we had theta in this direction initially, call this as the initial direction. Let's suppose this is the theta, and you learned some delta theta like this. So finally you will go to this direction. So this will be a theta nu. But on purpose, what we did is we said, in order to not make a huge mistake, so we'll just take smaller step. So step size will be this much. So we'll have eta of this delta theta, something of this sort. And then what will be that delta nu? So if we use parallelogram law of vectors, so this will be actual delta nu, this. So the loss function that we had, the loss that we had earlier, that is initial, and when we update, let's call it delta t, that is at t time t. So when we update this at theta t plus 1, so you had initially theta t, that is this is the parameters at time step t. Now these are the parameters at t plus 1, so the loss should be less. Okay, so this loss should be less than this loss, or this loss should be greater than this loss. This is what we wanted. So I said that basically means we have to approximate things. Okay, we have to approximate. So how to approximate now? So if you have any function, so if you have a function and you need to approximate that, you need to approximate that in the vicinity, in the neighborhood of a point. So what we'll do is we'll use Taylor series. We briefly define Taylor series. So basically what Taylor series is, it represents any function as an infinite sum of functions. So it represents any complex function as an infinite sum of polynomials. This is what it does. So you give it a function and it will basically give you an infinite sum of polynomial functions. Let me change this pen to make things more visible. I hope this is more visible now. Okay, let's start with so what basically we want to do. Let's suppose we have an f of x, some function like this. So we have some function f of x. So we want to now approximate it. Okay, so I'll show you the visualization first, and then slowly and steady what we'll do is we'll get to the core idea of the Taylor's function. So I'll now share the screen with you, where you will see that Taylor function, some graphs made, and then I'll tell you how these graphs came about, and what's the way that we are approximating these things. Okay, let me share this. So if you see this now, so here what we have done is, so we have a function given. We have started in this particular case. So in this particular case we have this function f of sine of x. Okay, this is what we want to approximate. So this is a function. So the function that you see in the red is the function f of sine of x. This is what we want to approximate. Now you know that this is a trigonometric function. So we want a polynomial function to approximate it. We want some polynomial function. So why polynomial functions? The first question should be that, why polynomial functions? Because polynomial functions, it is easy to sort of do a lot of stuff with the polynomial functions. If you have polynomial functions, so you can do a lot more stuff easily mathematically than if you have some complex function you have to deal with that. So it's better to have some approximations for other functions which is represented in terms of polynomials, so that we can do a lot of mathematics on it. As I said, that it become to deal with polynomial functions is a lot easier than the other functions. So here what I'm showing you is we have a function sine of x that we want to approximate. Okay, let's suppose we want to approximate that around this say around this center. Suppose we know the value at this, we know sine of 0. Okay, because sine of 0 is 1, so we know what's the value over here. So we want to approximate by the polynomial function. So as I said, this is a linear combination. Let me again start. So we have something of this sort. I'll keep on bringing this graph. So you have a function sine of x. Call this function f of x, that's equal to sine of x. This is the function that we want to sort of approximate, or we want some polynomial functions to approximate. So I said it is a combination of these polynomial functions. So the combination will start from c0 x0 plus c1 x1 plus c2 x square, something of this sort, and we are evaluating at x is equal to 0. This is our evaluation. So now what we want to do is we want to see, okay, if we are evaluating at, let's suppose if we have f of x. So let's suppose at some point 0, so it should be equal to this. So if sine of 0, this is f of 0, let's suppose, and this is our polynomial approximation. So let's call this p of x. So this is our polynomial approximation, okay, and this is our actual function. This thing that you see is the function that we want to approximate, okay, and we can keep on adding terms because this is an infinite series, so we can add more terms on in this. So now you have the sine 0. So sine 0 should be equal to f of 0. So that means, let's suppose if you take this, so here the x of 0 is 1, so I can just cut down this term. Now I want the value to be equal. Okay, at x equals 0, I want the value to be equal. So what should I do is, so the first thing I should do is I should have the value of the function, that's f of 0 should be equal to p of 0. This is what should be there, because I am somehow approximating this function. So this is my function by the help of which I want to approximate. So this is a linear combination or linear combination of these polynomial functions. So I have x0, x1, x2. Yes, questions?
Yes, sir.
So this is our function that we want to approximate. So if you see this over here, so this is our function, actual function, the ground function that we want to approximate, and this is our approximating function, because we want to approximate a function by using a combination of these polynomial functions. Now the first thing that I said let's suppose we want to evaluate this at x is equal to 0. This is what we want to do. So for that sake, so this f of 0 at this point should be then equal to p of 0. So that means if f of 0, if you see that it is called sine 0, so sine of 0, that is equal to 1. So similarly now p of x, so p of x, put value of x everywhere 0. So what you will basically get is, so you will have p of 0 c naught x0 is 1, so everything will be 0. So p of 0 will be c naught. That means this c naught is equal to 1. So in case of sine, so c naught is equal to 1. Okay, so I am approximating this sine by using this. Now I need to calculate the other coefficient c1, c2. So I will use the concept of differentiation here. Now what I will do is, I'll say the first derivative of these functions should also be equal, because at that point when I said at x equals 0, the value of the function at this point and the value of the approximating function should be 0. Okay, now one more thing should be, because we are approximating it around that point, around some point. Now what I'm telling you is that the first derivative of the function should also be equal to the first derivative of this. Okay, let me take the first derivative. So on taking first derivative, so this p of x, if I take the first derivative of this p dash of x, so p dash of x, because you will know that this will go to 0, this basically is, oops, so if you see this, so this is c naught x to the power 0 is 1, so this will go to 0, and I'll be left with this. So this will be equal to c1, so this will be equal to c1 plus sum of this, so this is 2c2 2x2 rather 2, I think c2 x2 x1, okay, yes, x1, and so on. Okay, when I put x is equal to 0, so what will happen is you will be left with this c1 only. Okay, so you're left with this c1, but with some coefficient. Okay, like here the coefficient was 1. Okay, if you see this, okay, we got 1 times c1. So in this case, what are you now? P of dash of x is equal to c1 in this particular case. Now you know that what is the derivative of first derivative, you also take the derivative of f dash of x. So f dash of x, basically the first derivative of this, so that is first derivative of sine of x, so that is cos of x. Okay, and cos of x, so evaluate it at 0, so f dash of x, f dash of 0 is equal to cos of 0, cos of 0 is equal to 1. So in this case c1 is equal to 1, because these two have to be equal. So we have, this is rather, initially we had c0, this is c1, now c1 is also equal to 1. So the approximation, now you are seeing that I am slowly filling the values. So c0, this came out to be 1, and calculations can be here and there, but I just want you to get the idea. This is also equal to 1. So you can again similarly expand this thing. So now the second derivative of this and second derivative of this should be also equal. So we are now playing in the world of derivatives. So derivative of this thing should be equal to this. Okay, so this is at a certain point x. So now if you want to generalize it, so you can have, let's suppose at the neighborhood at some point, let's say which is a little bit away from this x. So let's suppose at point a. So what we do is, then we center it around that. We'll write it x minus a. So this series will go like this. So if you have approximation p of x, so initially we wrote c naught plus c1 of x. So now if you have to evaluate this at some point a, so what you do is you want to center this. So you are saying x minus a, so that you shift that curve towards the left, so that this point a becomes the center now. Okay, so this is the reason I added the c1 minus this plus Now here c2 x minus a whole square plus c3 x minus a whole cube, and I want to come up with these constants c0, c1, c2, c3. Okay, I'll do it for a generic function now, as I did it for sine, so I'll do it for generic function. So let's suppose we have some function f of x. This is what we have. This is the ground function that we have, and this is the approximating function. So as I said, the function, the value of the function, let's suppose now f of a, so if you're evaluating at some random point a, so f of a should be equal to p of a. Okay, this is what it should be. Now f of a, if you see this p of a, you put value everywhere, so you see that f of a will be equal to a. Okay, so at this case, let's suppose we have this f of a, this will be equal to p of a, so you have this c0. So if I put these values at here, so if I put everywhere a, and this, everything will get to 0, and you will be left with c0. So when you are evaluating the function at that particular point, so you are evaluating at point a. Now I'm saying the first derivative should be equal. So by that I mean f dash of a should be equal to p dash of a. Okay, now you have to take a derivative of this function p dash of a. So how to take first derivative of this? So this will go to 0. Okay, this thing will go to 0. So now you'll be left with c1. Okay, and then you have this c1 plus. So you'll be left with 2 times. Let's suppose when you take a derivative of this, so you'll be left with 2 times c2 x minus a plus, and so on. You keep on taking the derivative, and when you put the value a over here, so whatever term you have this, so all of these terms will be equal to 0. So this term will go to 0, and all the other terms, because they have this x minus a, whenever you put the value x is equal to a, so a minus a will get 0. So you will have p dash of a is equal to c1. Okay, now you have to compute c2. So p dash double dash of a, you have to compute this, and this will give you c2. So in this case, if you see, so now c0 will be gone, this thing will be gone. So what will be left with? So I'll just now see the results from here. So when you compute p double dash of a, so you will be left with 2c2. Okay, so this should be equal to f double dash of a. This is what we want, and now we can compute c2 from this. So this will be equal to c2 will be equal to, so this implies c2 will be equal to f double dash of a divided by 2. Similarly, p triple dash of a, so this is equal to, so if you see, this is 3 multiplied by 2, because you do that n minus 1 to 1, so 3 multiplied by 2 basically, and then you will get some c3. So this should be equal to, so this should be equal to f triple dash of a, and now in order to compute this c3 will be equal to f triple dash of a divided by 3 multiplied by 2. Now if I have to see it at the nth level, okay, that is p nth, let's suppose nth derivative, if you take nth derivative with respect to a, so this will be equal to n factorial multiplied by cn. So you are computing the cn constant, and then this should be equal to nth derivative of the function at that particular point a. So that means cn, if you have to take any constant cn, the cn will be equal to f nth derivative of a divided by n factorial. So how many of you got this point? So this is the very important point for which we had the discussion. So how to combine this? Basically, I had to find these coefficients. I said in order to approximate any function, so p of x is equal c0 plus c1x plus c2x square plus c3x cube, and now I know the value of these things. So these are the values which I got. How many of you understood this over here? So this was when x is equal to, when we put at the center, when we put x is equal to 0. Now if I have to write it in a generic form, so how to write that? So I'll write that like this. So let's suppose you have p of a, some point of this sort. So you see c0 plus c1 of x minus a. So you know the value of x, and you want to now approximate it at certain value a, let's suppose. Rather I should write p of x, and then I'll put x is equal to a or something. So then I'd say plus c2 of x minus a whole square plus c3 x minus a whole cube, and so on. Now I know the value of these. So if I have to write that, so I can write now p of x is equal to at a certain point f of a, because I'm approximating that function at this f of a. So how I can write it? I can write it like this: p of x is equal to f of a, find the value of that point, plus f dash of a divided by 1 factorial plus f double dash of a divided by 2 factorial plus f triple dash third derivative of a divided by 3 factorial, because these are the coefficients. And now I can go till infinity. That's why it's called, it's an infinite sum. So this over here that you see is called as Taylor's approximation or Taylor series. So this is Taylor's approximation for any generic function if you are given this function. So I can just write in the compact way. So how I can write it that compact way is p of x. So if this is the function that if I have to approximate some f of x function by using this at some point a, so I can write it like this. So this is equal to summation n goes from, consider n goes from 0 to infinity. Now this should be equal to f of n at point a divided by n factorial. And yes, I'm missing one term, that is this x minus a. So I should keep on adding this. This is x minus a whole square. Okay, so these were the values for these constants. Okay, let me write it better way. I don't want to clutter it. So this was f of a, and then f dash of a divided by 1 factorial into x minus a. Basically the polynomial term. Then plus f double dash of a divided by 2 factorial into x minus a whole square, and so on. This over here was the Taylor series, actual Taylor series. So initially I did a mistake. I just wrote the coefficients. I also had to write these, keep on writing these. Similarly, when I wrote these coefficients, then this will be x minus a to the power n. So this is the compact representation of Taylor series. So this and this thing is equivalent. Okay, and when you have this f of 0, if you compute it, it's f of f is equal to 0. So what will happen is now you don't need to write this x minus a. So now the point is 0. So what you can write is p of x is equal to summation of n is equal to 0 to infinity f of n of a divided by n factorial into x. Okay, you can directly write it x to the power n. So this over here is called Maclaurin series. So you may have heard of this. So Maclaurin series. So if you are evaluating at the point 0. So how many of you understood this? So the question here was, why not to take n is equal to 0 to some finite number, if I can put the question like that. Okay, so because I said that this Taylor series or Taylor approximation is an infinite series, so that you can clearly see over here. So this is a Taylor series in an infinite sum of polynomials, so we take it to infinity. So now I gave you the generic Taylor's polynomial. So what you have to do in order to approximate, so what you should do is you should take a polynomial and you should write it this in this order. If you have sine of x, write this. So basically what you want for a function, if you have a function, if you know its derivative, if you can compute its derivative, that's why the function should be differentiable, it should be continuous. So in order to approximate it by using the Taylor polynomials, or you have these infinite sum of polynomials, the function should be differentiable, because you can see that we need function, let's suppose f of x is there, we need its f dash of x, we need f double dash of x, we need all of these things to approximate, and then these factorial terms are there. I think we have a question again. Yes, please. Okay, so now what I was mentioning to you is that if you have a function, so that function should be differentiable. Why? In Taylor series, we need we need to compute the differentiation of that function. So it is very much needed that the function is differentiable, so that we can do its approximation. Now I again take you to the window where we'll sort of visualize this and we'll pin it down to our heads. Now the formula that you saw, so I have done the similar thing in the Desmos calculator. If you see, I have done the same thing over here. So I have a function. This is my f of x, that is sine x. Okay, then what I have over here is, if you see this, so this is my function, then I'm saying nth is the nth polynomial of Taylor. So this n I have initially, this is equal to 0. Now I am approximating this function at this value. Okay, no, that's rather a. Okay, so what I'm saying is, so this a value a over here, the function that you want to approximate it. So this a is this value. So I want to approximate my function around this portion. So around this. Okay, this is the neighborhood. Let's suppose this is 1 and this is, let's again 1. So I am approximating my function around this. So this n is the number of terms you want to include. So we had that c0, then we had c1 x to the power 1, we had c2 x to the power 2. So if you are at n is equal to 11 or n is equal to 0, n is equal to whatsoever you write. So what you can do is you are basically cutting down this polynomial at that certain portion. Let's suppose I want to have c3 x cube. So I'll cut down my polynomial over here. So this n is the control where how many polynomials do you want to combine with this. So here I have put n is equal to 11 in this case. And if you again see this, so then I am saying this g of x. So this g of x over here, this is the approximation. So this g of x is the approximation. So this f of x, if you see, is the function that I want to approximate. This n is how many terms of the Taylor series should I include, and this a is at what point. Okay, at what point should I include this. So this right now a is equal to 0. So I should reduce the n. I don't want to take 11 terms. Let's suppose I want to take some 2-3 terms. Let's maybe initially start with 0 term. I don't take anything. So you'll see that nothing is getting approximated. So if you see this, so there is no approximation. So this is the function we are starting with. is f of sine x. Now what I'll do is I'll approximate it at a is equal to 0. Okay, I can just move it here. You'll see that the curve will get shifted that way. So let's suppose I'll include some first term if n is equal to 1. Now you see that there is a linear line is there which is approximating it, because you know, if you see the function that we saw in the Taylor series, that includes that c naught term, and that if you write, let's suppose write y is equal to some c naught. Okay, so if you let's suppose only include c naught, that will say like you have included the 0 value. So 0 value was just c naught, so this was this, so you saw a straight line like this. So now if you do this, so if you take n is equal to 1, so you are taking the first order polynomial also. Now you're taking first order, that is a linear polynomial, so you can see this line over here. Now the important thing over here is I am at x is equal to 0, you see. So this is trying to approximate this portion. So only with just a linear line, you can see that it's a pretty good approximation. Around this line, around this value 0, this line is giving good approximation. Okay, now if I increase this, you will see the approximation will get better and better. Let me just see that. So if I include now, let's suppose second order polynomial also. So I was including first order and now I'm including second order. Now what you can see is nothing is there. Okay, you didn't see any change. Basically, maybe that coefficient before that got 0. That is, c0 had some value, c1 had some value. Now when I wrote c2, second order polynomial's coefficient probably is 0. Now I hope that if n is equal to 3, so you see this, it's again approximating. It is doing a pretty good approximation around this point 0. You see, so this a is the value, or which is showing around which point are you doing the approximation. Again, going back, I can show you if I move a, you can see that this is moving. Okay, let's suppose I want to approximate around 0.4. So now you see this is 0.4 roughly. So here if you see this is 5, let's call this as 0.4. So this is approximating roughly over here from here to here. And you see that in the neighborhood it is doing a pretty good approximation. That means the more terms you include, the better approximation you will get at that particular point. So if I increase, let's suppose to n is equal to 5, 6, you can clearly see that it is doing approximation. Let me do it to 0 to better visualize it. Okay, now you see this. So this is n is equal to 8, n is equal to, let's suppose 9, 10, 11. So you see it is doing a better approximation. The more terms in the more polynomial terms you include, you can have first degree polynomial, second degree, third degree polynomial, and here we have taken the polynomial to 11th degree. You saw that it is giving a pretty decent approximation. And you can do it for other functions as well. Okay, and you see the Taylor series is defined as the way I did it. Okay, similarly you have this function, you have this Taylor series g of x, h1 of y1. So y1 is defined like this. Okay, y2 is defined like h, and h is defined like this. Okay, this is basically the function value at that point in time. So now I can take function, say some cos of x, or maybe some other function, some cos x, because these functions are not polynomial. I want to approximate these functions. And let's say if we have to take, say n is equal, if we take till third degree polynomial, basically that's c1. You see how good approximation it is. It's a decent approximation. You see over here around this point 0, because a is equal to 0 now, around this we are doing the approximation over here. Yes, please, questions. Okay, on popular demand we'll see this for L n of x. Okay, you can see this. So now let's say what is the approximate. I can't see that line. Because it's defined for positive, I'll have to take positive value. So you see this, let's suppose at some certain point we'll take some positive value. So now if you see this, it is trying to approximate, but it is not beyond this point. So I'll take you to that concept as well. So it is approximate till here, so it cannot approximate all the functions. So we have what's called as radius. So here you have this radius approximation. So that is one of the limitations of this. So if you do it with log of x and certain functions, so because this function is not converging there, so we'll get to this. This natural log is a case where you can approximate it in this area. Let's suppose from here to here it approximating, no matter how many better terms, how many big terms include now. So I start, let's suppose from there, I started with n is equal to 0. So when I include the first order polynomial, this is the linear approximation. So when I said quadratic approximation, so it is like this. So after this, if you see, it will keep on fluctuating. Okay, it is not getting better. Basically, it is not, the approximation is not getting better. This is one of the limitations of this. There are certain functions like this natural log, so where you will see no matter how many terms you include, here this series is basically divergent. So you might have heard concept of convergence and divergence. So here you see that this series is diverging after a point, and this radius over here, if you see, like, so from this point 0, if I can make it, so from this point we call it, we have this radius in which it works. Okay, we'll go to that as well, but I want you to understand, have you understood how this Taylor approximation works for many other functions. And you saw the example that in the natural log of x, it cannot approximate the whole function, okay, and it can approximate the function to certain points only. So have you understood this? Okay, now let's take an example first. Okay, the question was what I meant by it cannot approximate all the functions. So I will see it with the exponential functions first. So you have this function f of x, that is e to the power x, suppose. And the best thing about e to the power x is you have every derivative. So f dash of x is again e to the power x. Okay, f double dash of x is again e to the power x. So all of these things now you have. So if you have to approximate e to the power x, so what you can now do is you can directly see that let's suppose at x is equal to 0. At x is equal to 0. When derivative is e to the power x, so e to the power 0 is 1 everywhere. So what I can say is the coefficient will start from 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Okay, you see this. So this over here, so if you now evaluate its value, let's suppose you evaluate the value at e to the power 1. So what will happen is you'll say 1 plus 1 square divided by 2 factorial plus 1 cube divided by 3 factorial. So you know this series will sort of converge to value 2.71. Okay, because the value is getting closer to something. But if you do not have a series, so if you in terms of log x, if you now write the approximation of log x, you will see that it's a divergent series. It won't converge to a singular value. Okay, so that's how I can briefly explain this. So but there is a proper theory of this. So this is the limitation. I'll just highlight. So Fahad asked a really nice question, so I got to also write the limitation. So what is the limitation of, otherwise I'll miss it. So limitation of Taylor's series. So well, the first limitation is it is local approximation. It does the local approximation. What is the meaning of local approximation? The series is most accurate around that point. If you have, let's suppose, at x is equal to a, so you will see that it is accurate at that. As x moves farther and farther, you will see that this approximation diverges. So literal meaning of divergence basically is it won't get to the value that you want it to be. So convergence basically means so it is having that value which you actually want. So in this case of e, so you have the value e to the power 1 is this. So the more terms you include, you see that the series is convergent. Basically, it is giving the exact value that you have. Okay, that is the meaning of convergence. The meaning of divergence is if you, let's suppose, want a particular value, but you see this approximation is not getting to that value, no matter how many terms you include. So that will say that this series diverges. It is not converging. Basically, converge means it is going to that point. Diverge means it's going away from that point. It is not giving the accurate value of that point. So the first limitation is that we have this local approximation. As you go away from this point, you will see this series diverging. And the second thing, which is very important related to this, so second thing is we have this radius of convergence. So if you have this interval, the interval where the series converges, it depends on the function. So as we said, in terms of e to the power x and sine of x, it converges for all x. But in terms of, let's suppose, log x, it converges to a certain portion only. So the interval at which this series converges basically gives the exact value. So that interval is called as radius of convergence. The radius of convergence. This is again one more limitation. Why is there a limitation? Because you cannot make this series converge because this radius cannot be for all x. But you saw for e to the power x, for sine x, the whole interval is radius. Basically, whole x is the radius of convergence. But in terms of log x, probably it is 0 to 1. Only that thing is approximated exactly. Basically, the series converges there, and for other intervals it diverges. I hope I answered the question, and we also got to discuss two more important things. Now we saw that how can we use Taylor's series for approximating a complex function or any other function which is not polynomial in terms of polynomial functions. Now, why are we interested in this Taylor's series? Because we are solving the problem in which we have to find this direction of these, the direction of weights and biases. So in which direction should we move on that error surface? So you had that manifold or terrain or surface. So you had that surface and we wanted to move. We said that it is as if we are blind. So we know the value at that particular point. So we could have done this, we could have constructed the whole error surface, but it is impossible for us to construct whole error surface because the first thing, it will be high dimension, and second thing, there will be infinite number of points. So it is better we use some approximation. So we have this surface will be a function. So it will be a very complex function. And the good thing is we want to see its neighborhood. We want to see its vicinity. F we know a value. Let's suppose this error function is some e of x. So this is our error function. So consider we chose some point randomly, some x random. So this is our point where we started at. So we can compute error at that point, x random. Now we want to see how does the function behave in the vicinity. The good thing is we can do it by Taylor series. We can approximate the vicinity by using Taylor series, and then by using Taylor series we'll see, okay, which direction should we go. Okay, should we take let's suppose this step, what should be the values of this, what should be the value of this delta theta, basically this w, delta w and delta b. So what should be the value? So this is where Taylor series kicks in. So again, to make notations clear, so theta we have is this weight and bias, and then delta theta is delta w comma delta b. This is basically the change in parameters, what change should be done. This will give you the direction. And then eta, which we saw, so this will be a small positive scalar. So this is small positive scalar, and basically this is called learning rate, which we saw. So we'll have a detailed discussion on this, but still I want you people to know this is called learning rate. And then you have this theta nu. So this is the updated parameters. So updated parameters. So this is initial parameters. Okay, and this is this is rather giving us the direction, the change in parameters. This is what we want. Now the thing is, we have this loss function now. So this loss function, we have to compute it, we have to approximate it in the neighborhood. So we know, say, L theta. So we know how to approximate it. So the initial theta was theta, and then how to approximate, we'll say we'll add some nu times this delta theta. Okay, instead of delta I'll write u. So this delta theta I can approximate it with u also. U is this, basically I don't want to again write this delta and delta. So what I'm saying is you have to compute, this is the loss function after the updation. So the question is, you had some initial loss function L of theta, so now you're updating it with this rule. So you're saying theta plus eta is some learning rate, because we don't want to take full step. The problem with that, we can be wrong, so we want to be less wrong, so we'll take less step, and this u is the change. So now you can approximate this. So you can approximate this by using Taylor series. Okay, and Taylor series is not only valid for just one variable. So we have seen this in only one variable case right now. So we saw this at, let's suppose, at x is equal, at only x. So we had only one variable in this. So you could have multiple variables. You could have function in 2D, 3D, ND. So you could have any dimensional function, and you can see it in the neighborhood. So in case of, let's suppose, you had the function like this. So you're approximating by using a line, and then by using some curve of this. Okay, so it hugs the sort of function, or it overlaps the function at that point. So you can have a complex function in which you have a surface. You'll have a surface like this. So at that point, the line will be a plane rather. So you can have a terrain of that sort, and you can approximate it accordingly. Taylor series is equally valid in other dimensions as well. Okay, we just discussed for the one dimension case so that you visualize. You can visualize it in 2D, 3D, ND, howsoever you want now, because mathematics gives you tools to again apply the same rules on ND also. You can visualize maybe in 1D and 2D. Beyond that, you cannot visualize. But we have the tool. Taylor series equally applies to all the dimensions. Now we have this L of theta plus this is our updated parameters, and this is where we want to compute the loss. Now we can approximate this updated loss by using Taylor series in the neighborhood. So now what will this be equal to? So this will be equal to L of theta, okay, by using the similar rules, and then plus this eta, and this, you know, we have a vector. This is not a single number now. This is a vector, and we need to perform multiplication. So in this we can see ut, and then we can say delta theta of L of theta. So what is this now? So I'll explain the other terms as well, then plus. So this is dot product, because this is a vector now. So this over here is a vector. So this over here will be a vector. So I'll explain these terms again. Just hold on for a second. So this will be eta 2 divided by 2 factorial. Okay. And then we'll have multiplied by u transpose. This is, I think, rather is nabla of L of theta. Okay. And u, and so on in higher order terms. So now this thing, we have two, at least here we have two parameters, w and bias. So you'll have w naught, w1, w2, you can have any parameters. So if I talk about this, let's suppose this. So if I talk about this portion over here. So let's suppose we have this quantity. So you have quantity w square plus b square, something of this sort. So now you do not take derivatives directly. What you do, you take partial derivative. So because both of these quantities are variable quantities. So you now want to make one quantity constant and then take derivative with respect to other quantity. So let's suppose you can take derivative of this. So I can take d by dw of this function. Okay, so that is a normal derivative we take if we have function in one variable. So there is only one variable, but you know this function at least is having two variables. So now at that point we'll keep only one variable as variable and all others will be treated as constant. So that's called as partial derivative. We will not calculate the whole derivative, we'll compute partial derivative. So what we'll do is we'll say this dou divided by dou w. So this is the derivative of this expression with respect to w, treating this b as constant. And similarly we'll have dou divided by dou b. So this will be partial derivative of this expression with respect to b. So that will assume w to be constant. So this will be equal to, so once you assume this as constant, it will be 0. So you'll have this as equal to 2w. And this, if you treat this as constant, this will be 0 and this will be equal to 2b. And now if you sort of if you put them together, you have this 2w and 2b. So basically you had a vector which is dou divided by dou w and dou divided by dou b of some function f of some function f. So this over here, these are called as gradients. So what is a gradient then? It's a collection of these partial derivatives. So that is what is over here. Okay, and then you know what ut is, because ut is this delta w and we have delta b. So that's why I wrote it as a product. Okay, similarly for this. So now you have this for, so this over here, now you have ut, one vector, and then you will have to take derivative of derivatives, double derivative. You take double partial derivative, you'll have Hessian. So you'll have initially this, let's suppose d by dw, then you'll have d by dou b. So when you now take second derivative, so second derivative will be something of this sort, dou square divided by dou w square, dou square divided by dou w dou b. Okay, then dou square divided by dou b dou w and dou square divided by dou b square. So this over here is called a Hessian. Okay, so what is a gradient? So gradient basically is you compute the partial derivatives and put them in a vector. So when you have this vector in which you had these two derivatives, now when you take double derivatives, so you get a matrix of this sort. So this is called Hessian. Okay, usually in machine learning you'll only use maybe till the first, you'll use till here. Okay, you won't use approximation maybe after this, because this eta anyway is very small. This eta is 0.001. So the more terms you include, the higher powers you get, it will become more smaller. So you usually omit these terms. So we consider that this approximation is good with the first order derivative itself. So in the first order derivative we have this gradient. That's why it's called gradient descent. Okay, you understood the concept of gradient. So what is a gradient? So you take these partial derivatives and you club them into a vector. So this is called a gradient. So when you have to compute double derivatives of this with respect to these different parameters, then you get a matrix which is called as Hessian. So can I assume that you understood Hessian? And okay, now I just wanted to reiterate this, that you are now better equipped to take a decision of cost function, because we are using Taylor approximation in gradient descent. So it is better when you see that, when you approximate it, so you should have a function which is differentiable and the function which can be approximated by the Taylor series beautifully. So now you saw this. So we saw this is over here is our gradient and this over here is our Hessian, and we'll remove these terms. We'll be only worried about this term. So again, I'll write this. So you have loss function at the updated parameter. You see how I will read these equations as plain English. Okay, so loss function at the updated parameters is equal to loss at the initial parameters plus you have this learning rate. Okay, and then you take the dot product of this with the gradient. Okay, so this was the function that we wrote over here. I don't want to mess with the notation. I want to exactly write the notation as I wrote it. Okay, there is nothing scary. And after this, what I did is this is approximately equal to this. So I can even, this is approximately, not exactly equal. This can approximate it. So, but the goal was this loss over here should be less than this loss. Okay, so this was my goal. So if I see, I can say this theta of u, that means the updated loss minus this loss. Okay, this loss should be less. This should be negative. Okay, this should be some negative quantity. Okay, this somehow should be a negative quantity. That means this over here should be the negative. So this should be some negative quantity. So if I write it like this, so eta of ut, this L of theta, basically the gradient. Okay, this over here should be the least, and we want it to be negative because you know that this is approximately equal to this, and we want this to be negative quantity or less than zero. Less than zero, basically negative quantity. Now what I can do is I can take a dot product. So if you want, we basically want this to be less than zero or negative. So you want eta of the CUT. It becomes even hard to write, not just to read hard. Like this is a simple thing, which is saying that learning rate, and then you have this change in those gradients, and you have this derivative of this basically, and they should be equal less than 0, and you know what this means. And now what we want is we want to choose the optimal direction. So if you take dot product of this, if I take dot product of ut delta theta loss function of this, so what will be the dot product? You take magnitude of this, magnitude of this quantity, okay, dot cos of, let's suppose call that we have angle beta between them, and cos of beta. Okay, now if I want to, let's suppose I'll take cos of beta. So what is cos of beta equal to? Cos of beta is equal to ut delta theta L of theta divided by magnitude of this, magnitude of this. Okay, this is how cos beta can be defined. But you know, cos beta, the least value it can have is -1. Okay, the least value it can have is -1. So what you can do is now take this term, you know, this dot product. So over here, this is the term that we have if we remove the eta. Okay, because eta is a positive number. It doesn't matter now. So this thing is eta. Now this thing, let's suppose, is the term that we want to have the least value. We want to have it less. So what basically we want, we can have that this u is equal to, basically we have u transpose delta theta L theta. Okay, so this is cos beta, and cos beta can have it is a bounded value between between -1 to 1, and we want this one to be there, and we want this value to be -1. So if you want this value to be -1, let's suppose if you want this value to be -1, because we want it as negative as possible, that means these two things should have angle 180 degree. So the beta angle should be 180 degree between these. Okay, once you have the 180 degree, what's the meaning of that? That means ut should be equal to negative of delta theta L theta. That's how we can get negative. So that is why we go in the direction opposed to the gradient. So when you see this, so you have theta and you have to update this parameter. So what you do is you take initial theta, then negative of, you say eta, and then you take the derivative, partial derivative, whatever you take. So that's why you go in the negative direction of this. Negative direction basically means you want it to be negative. Why do you want it to be negative? Because you want this term to be less than 0, this term to be negative. And why do you want this term to be negative? Because you want the new loss, it should be less than the original loss. You want to decrease the loss. So that is why you should go in the opposite of the gradient. The direction basically you should go is, so this u, the u transpose that you see, this should be equal to minus delta theta. You compute the gradient. Once you compute the gradient vector, you just write the minus sign in front of that. So that is the direction you should go. Now what is gradient descent telling you? Gradient descent is telling you compute the gradients and go in the opposite direction of the gradient. So this is the direction the gradient, this is the direction, and opposite basically means you should go to the negative of that gradient. Okay, that's why it's called descent. Ascent basically means, so gradient gives you the ascent, it gives you where you should, the value will be more. And what is the negative sign doing here? It is telling you have to descend, you have to go in the opposite direction. So whenever you have to update these gradients, you go in the opposite direction of these gradients. Okay, whatever gradient you compute. So how many of you are getting this point? Okay, now we'll move ahead. So to summarize here, what gradient descent is telling you, what this Taylor approximation and everything told you, that whenever you are updating, the direction is basically you have to go opposite to the gradient. So whatever gradient you compute, you have to go in the opposite direction of that. Now how to update the parameters? So by this equation, the equation that you got an equation u is equal minus of the gradient, minus the gradient of the loss function. So what is this gradient? You know, it's a vector. So you have to get this theta nu. So theta nu basically is theta plus eta of this learning rate of now minus delta, basically the gradients. Okay, the initial theta and the gradient. So simply you can write theta minus eta of delta theta in this. So this portion over here, this is theta nu, this is the updated parameters, and these are our initial parameters. This makes sure that we don't overshoot. This is learning rate. So learning rate makes sure that if we did a small mistake, let's suppose if the direction was even not exact, so we can not commit a bigger mistake. So the learning rate is usually a positive number which is close to 0, and then this over here, if you see, is the gradient, and this is telling you go in the opposite direction of gradient. So this is telling you opposite direction. Okay, so now what we have to do is, if you had initially theta was equal to this weights and biases, so this was your theta. So now what should be WP plus T plus 1? So initially I said we have WT and BT. So this is theta T, this is WT and BT. If you have theta T plus 1, that means we have WT plus 1 comma bias T plus 1. So how to update this? So w t plus 1 will be equal to initial w and then minus eta of dou L, the loss function that we had, by dou W, and this should be evaluated at W is equal to WT and bias is equal to BT. And similarly for bias term, this should be equal to, the updated bias should be equal to the initial bias minus the learning rate and compute the gradient with respect to the bias at W is equal to WT comma bias is equal to BT. This is what you have to do it. So I pinned down everything. So how many of you understood this? Now finally we can write gradient descent algorithm. The first thing, it again is an iterative algorithm because it is not the algorithm which gives you the closed form solution. It is an iterative algorithm which you will iterate continuously. So how does the algorithm go? So algorithm, you will initialize something. So once you initialize, and you will give some maximum number of iterations. The maximum iteration, let's suppose, is equal to some, say 1000 or something. So you have some number of iterations. So you say that you keep on doing this while this iteration is less than, let's call this t is the iteration which is keeping iteration count, t is less than 1000. So total is going, compute the gradient. So you have to compute gradient. So what you will do is you will compute gradient. So what's the meaning of gradient? So basically you will compute this nabla of W, that means dou L by dou W, and then you will compute change in this, and this will be dou L by dou B. Okay, you compute these partial derivatives, and what is the point you should compute them at? At WT and BT at the previous step, and then you update parameters. So you update. So how to update this? So update t plus 1 should be equal to WT minus eta of W, and this should be bias updated is equal to bias initial minus eta of this. Okay, and then increment this t. Okay, and keep on doing this until the end. So each time you'll also, after this, you'll compute the loss also. You'll compute the loss and see is it actually happening. And this is ensuring that your loss function basically is decreasing. This is what is making sure that you have this. And this over here is gradient descent for you. So this algorithm that I wrote in some fewer lines now. So this is your gradient descent algorithm. Now, why did we do this? The thing that we did it because we were doing a problem. The problem that we were doing is we had some points. We had some 3 points like this, 1, 2, and 3 points. Some points were given like this. And we are fitting sigmoid neuron on it. We are fitting some sigmoid curve. So we want to fit some curve of this sort, some curve of this fashion on this. Okay. I can make pretty terrible curves, but this is what we were trying to fit. And initially what we did, we did some guesswork. Okay. We initialized randomly, then again initialized randomly, we kept in history, and then we were in the hope that if we run it for enough times, what will happen is we will maybe hit some optimal W so that the error is least in that. But now you have a principled approach. You have an approach in which you are sure that you are going in the right direction. Okay, but the problem again with this gradient descent is it will give you the local minima. It is not sure that it will give you the global minimum point. Why? Because it depends on initialization. So many things depend on initialization. So I'll say how much losses depends on initialization. I'll just write this term so that you understand what I'm saying. And now you also heard there are a lot of initialization. There's a lot of work that people have done on this. So how to do better initializations. Okay, there are a lot of methods that people came up with because they were getting stuck. They were getting stuck in some local, and that they're called as barren plateaus. So there is a problem which is called as barren plateau. Basically means it. So it was something of this sort. So you had an error surface which was something of this and something of this, and let's say you got stuck in this. This is the barren plateau now. So there is no way coming out of it. So you are not learning. Why is it called barren plateau? Barren is opposite of fertile. So fertile basically means that you have possibility of learning. So in this case, it's barren plateau. You cannot come out of this because you're not learning it here. Okay, that's why you have a lot of better initialization so that you, at least let's suppose if you are here, if you're initializing here, you're pretty sure that we'll go here. If you initialize here, you're pretty sure you'll go here. But what if you randomly initialize and you got stuck over here? That's why you see a lot of research being done on better initializations also. Okay, so we'll also cover that in history, that people have done work on better initializations. People have done research on these, coming up with these algorithms as well. Now we have this gradient descent. It is better for the single sigmoid neuron that we saw. But when we have multiple layers of these neurons, then we need back propagation. Gradient descent is not enough for learning. We'll see that also. But here, what I said is we were actually solving this problem. Now we'll use our gradient descent approach, the thing that we did now. So we'll use this in order to solve that problem. So the data set, you know, I don't need to give the data set. So the data set that you had is the data set of 3 points. So you had data in which we had points like xi, yi, and we had 3 points in this case. Okay, and endpoints. And then we had a function sigmoid. So we had sigmoid function. Sigmoid was 1 divided by, this was data, and then we had learning model or function. In that model, it was 1 divided by 1 plus e to the power. Then we had w transpose x plus b, something of this sort. And the loss, you know, the loss function was mean squared error loss. This was our loss function. Now what we have to, you have to compute this. You have to compute gradient, and for the computation of gradient, you know how to compute the gradients. Okay, how to compute the gradient of the sigmoid. So you can easily do that. So once you compute the gradient, so I'll tell you one thing here. If you have sigmoid of x, so if you take the derivative of sigmoid of x, so this comes out to be sigmoid of x into 1 minus sigmoid of x. Okay, very good function. You see, derivative. Then we need this derivative. So we need the derivative of this. We might need second derivative also. So this is the sigmoid function, and you can do it on pen and paper by yourself also. So you have function 1 divided by 1 plus e to the power minus x. If you take derivative of this, it will be like this. So you have this function sigmoid and its derivative is this. Now we know the derivative also, and now we can apply the gradient descent algorithm. Okay, let me code everything again, and then I'll again show you the visualizations. There are a couple of things now left in this. First, I'll do this error computation by using this, and you will see that we went to the directed way, and then I'll show you some visualization. Give me a second. So we'll see the previous code for once, and then we'll see today's code. So you see, in the previous code, we initially had this sigmoid. We sort of defined sigmoid, then its compute MSE, then we randomly generated some 3 points, and then we had here, let's suppose 1000 iterations, and then we did all the things, and we by basically guessing these W's and weights and biases. Now today, because we have gradient descent, so we'll almost do the same things. Okay, so the things that we will be doing is basically, we'll again see the same things that we did there. Again come up with data and all the other things. Give me a second. Now starting with the code. So again, I will import and write sigmoid. So if you see it over here, okay, I believe it's visible. So now you see this. So importing this and defining sigmoid, and then what I'll do is I'll again do the same thing. I'll compute the MSE. Okay, this is my mean square loss. So what I'll do is I'll also compute gradients, because I have to compute gradients. So okay, I'll explain this computing gradients. Nothing, whatever I did on the paper, you have to do the similar things. We come up here. So now you have this important part, that is you have to compute gradients. So in this case, what we did is, so you have compute gradients, you take this x, you take y, and you take this weights, and you take biases. Basically, this is the initial data, that features of data that we have, and then you take this y. Let me again zoom it so that you see it. Okay, I hope this is clearly visible now. So you have this x is the features, y is the target, w is weights, and b are the biases. So predictions basically is, this is forward pass. So you just do sigmoid of x times b, x times w plus bias. Okay, and the error is basically prediction minus y. Now you have to apply, you have to do the derivative of this. So what you do is prediction into 1 minus this. This is the thing that I wrote. Okay, so if you have to compute derivative of sigma, so if you have sigma of x, so the derivative of this is sigma of x into 1 minus sigma of x. This is what derivative over here is written as, predictions into 1 minus predictions, because this is what predictions are. Okay, predictions is your sigmoid. Okay, this is prediction derivative of that. Okay, and now we have to also, give me a second, we have to also write this. So now dw is np, mean 2 times error into sigma, because you again take a derivative of this. So this is db is this, so this is what dw, this is how dw and db is computed. Okay, pretty standard. And then you return this dw and db, because based on these we'll make the updations. Now we'll generate the data set. So data set, and then we'll do the iterations, and then we'll keep loss history. Again showing you this. So in this, what we can do is now generate this data set with 3 points, the points that we earlier did, and the iterations here. This is 500, and the learning rate is 0.1, and we have w, and we have bias, and then we will keep this history and the loss also. Okay, now let me run this algorithm. So I'll paste the code by the help of which I can run the algorithm. Okay, if you see this, I am plotting also. So here I'll explain you more. So we have this compute this, and now we'll apply the gradient descent algorithm. This is our gradient descent algorithm over here. So you have this DWD compute the gradients. It will compute the gradients that we have, and you know how to compute gradients. And now you have this update rule. So update rule is W learning rate into these parameters. So you are updating W and bias, and you are computing loss. So you again have this compute loss, and you are appending this history, and you are having this, and you are printing after every 50 iteration, and you will see that it is better than random. Why? Because you will see in each iteration there is a high possibility that you will always go to the loss where you'll always go in the direction where you have lesser loss. So in the random case, you'll sometimes go here, you'll sometimes go there, you'll have increased loss, decreased loss, but it will be random. But in this case, you are making sure that maybe more than 90% of the times the loss is always going towards the point where you have at least local minima. So it is continuously decreasing. That's what is written in the code. And then what I'm showing is, this is just the plots. I'm plotting the best W and best B, and then also plotting some history, and then plotting basically the line. So if I just run this code, now seeing this initially, so you see this is the stepwise updates. How did the updates happen? So we started with iteration 0, randomly initializing this -1, 4, and MSE was this, and then we updated W till 50 iteration. You see this loss. It is starting with 0.2, then going to 0.07, 0.01. You see continuously decreasing the loss. Okay, and the best fit that we got is this. Bias was this, and it is basically we are now navigating in a proper direction. Okay, even if we are blind, because we know the vicinity around us, so we can update the things accordingly. And you see the best curve in here. So you see this is the best curve that we have, and in gradient surface, so the line is not visible, but here you can see that this is the gradient descent path that was taken. Okay, I hope this is clear for everyone. Can I assume that this is clear for everybody, or any questions? Do we have any questions here? The question asked was, should we keep this learning rate as constant? Because in this case we put learning rate eta is equal to 0.1. So it's always the case we'll point it equal to 0.1. So I said the crux that we had this learning rate is because we don't want to overshoot in learning. So if you have a function of this sort, so you are at this point, say, and if learning rate should be set in such a way so that you don't overstep. Let's suppose if you have learning rate maybe something and you shoot to here, you directly go till this point, or you go to this point, so you're missing that optimal point that you wanted to reach. So you want to make sure that it is taking slow baby steps, it's taking slow step, but the steps should not be so small also it will not learn at all. So when you are training a network which has already learned a lot of stuff, so the better thing is keep learning rate very less. And if you are even making a mistake, the mistake they don't accumulate, and you will still get the optimal point. That's the crux of learning rate. So usually you will start it with 0.1 or 0.2 or something of this sort, which is nearly equal to 0, but not exactly 0. And the more the network is learning, so you will decrease this learning rate in here. And as I said, we'll have a separate discussion on learning rates and optimizers, how they adapt this learning rate. Okay, one thought, food for thought is that can there be something better than a gradient descent? Or can there be something at least which can do some sort of gradient descent, but not the gradient that we saw? Can we do something else also? Okay, by not computing the gradient. Okay, so the example that I gave, you have a point over here. So what you should do is you take, let's suppose, some points in vicinity. So once you take these points in vicinity, so you'll see which other point has the least loss. Suppose this point is the least loss, so you will update this point over here. Now you'll forget about all the points. So you'll take this point into consideration and have the points in its neighborhood. Okay, what you can do is, let's suppose this is the point which now gives the least loss. Now you update your point to this point. Okay, this is your new updated point. Now you again have these points in the vicinity and compute the loss. So what I said, this is called as local search. So gradient descent is something different, because in that we compute gradient and descent. The gradient basically gives you the direction of ascent. So here you descent, that's why it's called gradient descent. That is the algorithm. So in gradient, if you have a point, you want to compute the direction where you should go, and direction basically is in the opposite of the gradient. You descend the direction so that it gives you the lowest value where the function has the least value. Okay, so now I want you people to see at this animation. I'll share the screen over here and you see this animation, and so that this gets pinned to your head once and for all. Give me a second, I'll share that. Is it visible? I hope so. Okay. So now what I'm showing you over here, so let's suppose we have to learn something. So we have to approximate this value over here. So now you see this is our error surface. Okay, if you see the thing that I am rotating over here, this is our error surface. Okay, the values right now are values right now. So here we'll apply the sigmoid because we have a lot of these functions. So I'll apply sigmoid. So this is my sigmoid function. Okay, and corresponding loss function of the sigmoid is like this. This is the loss surface. Okay, so let's suppose if you see this function, I think it's visible. Now I can change these parameters a and b. Okay, so if you see I'm changing a and b, you are corresponding seeing there is a point on this. So if you see this point is also getting changed. So once I'm changing this a and b, or that is w weight and bias. So this is our w and this is our bias. Okay, I'm changing these, you are seeing different losses. Okay, here I am approximating some function. Let's suppose some target function, or in this case is sine function. You can have some other function also. You can have some cos function, Gaussian function, whatever you want. Okay, and I want to approximate that function by using a single sigmoid. So I can have multiple sigmoids, but in this case I'm having a single sigmoid, and these are my data points. So the blue ones that you see over here, this is the data point that we have sampled. We have sampled data points around this, and we want to sort of approximate our function around these points. This is our weight, this a, okay, and this is our bias. So this point b is our bias, and you can see that when I'm doing the change, so you can see this, I'm also navigating the surface. Okay, I'm also navigating the surface. Now look at the surface. I'll run this algorithm. Okay, I'm using a learning algorithm to be gradient descent, and we have local search as well. We'll see both of these. Okay, now let's suppose we'll train, and you'll see both. You'll see you have your eyes on this curve and have your eyes on this point as well. You'll see this point also moving. Now run it, train it. You see this point? It is going towards a particular direction. It is following a path, and you see this curve is getting approximated somehow towards these points. You see. Initialization was quite bad, so it is approximating quite badly. Okay, now it is adjusting some bias over here. It's still going there. But again, I'll show you the local search. Okay, let me just stop training. So if I show you the local search I said, let's suppose if this is the curve, and I'll adjust these weights and biases again. Okay, say this is the curve, and this is, and I'll just close this train. So I'll do with local search. So let's suppose this gradient descent, I'll click on local search and train. You'll see what it does. It computes certain points. You see, there should be a way to zoom it. Oops. Let me zoom it in a proper way. You see this. You see, I'll again make it. This B is here. You see how this local search is working. I hope you are able to see it. It's computed local and it is going somewhere. Well, let's suppose I'll stop this, and you see it approximated. It's also approximate the points that we have over here. The points that you see over here, it's approximating local search. And if you see gradient descent, let's suppose I'll make a bad approximation. I'll take it where it has this is the least fit. This is a very bad fit over here. If I check, let's suppose gradient descent on this, so you'll see gradient descent is taking one step at a time. You see, it's taking steps. I'm zooming it so you have to see it. But if I'm, let's suppose, changing this to local search, you see what is happening. It's computing points nearby, and then you also have a look at this function. It is trying to approximate. See, it has approximated this, and it is going towards the optimal point. You have your eyes here also, your eyes here as well. Okay, let's stop it, and I'll show one more time. Let's suppose I'll do a misfit, something of this sort. So this is the misfit. The point is over here. I'll use gradient descent. So now what gradient descent will, it will not compute the points. So what will it do? It will compute the gradients. So I'll train it. You see this, and you see it got in barren place. It is hardly moving. You see. It's moving very slowly if you see over here, because it's taking those. We also have somewhere here we can control learning rate as well, so that it takes longer steps. But if you see the one difference that I saw, local search was going a bit faster. It was jumping over, but gradient descent is being very careful. You see? Now in this case, it is finding new optimal point. It is going here, there. I don't know which path will it follow. You see the function as well. And this function is pretty simple, and this is pretty simple, and you can find it is mostly going in this direction. But if you have a quite complex function, you can have a lot of local minimas. Is it clear?